Hey, let's talk about section 5.3. We're talking about definite integrals. We're going to talk about antiderivatives. Big idea here, and that is that um, there are rules having to do with definite integrals. These expressions that are supposed to represent something having to do with the area between curves and the x-axis. So, for example, if I have a function going from A to B, you know, I've got this expression that will represent the integral from a to b of f of x dx. Well, what happens when b is listed first? Sorry, what happens when b is listed first? Now, the height of each individual rectangle in the Riemann sum remains the same, but the dx, which is a stand-in for the delta x, b minus a over n. Well, when you flip these, this ends up being a minus b over n, where n is the number of rectangles, but a is smaller. So this expression is negative. So what we end up getting is the opposite of the value that we have if the limits of integration are quote unquote in the right direction, right? So that hopefully should make perfect sense. Oh, the integral from a to a of anything ends up being zero. Why? Well, it's the area from a to a. Well, there's no area there. It's just a line. This idea that if we have a constant, we can pull that constant out. Perhaps that should make sense that if the height of each rectangle is k bigger than f of x, then we can just find the area with f of x and multiply it by k. Um, Also, that the sum of these integrals can be written, the sum of the integrands, the sum can be broken up into two integrals. Okay, actually, you can see that that seems to have a similarity to the same rule having to do with derivatives. Same with the difference. Um, if there's a difference between two functions, we can think of it as a difference between two integrals. Okay. This next one, f max and f min are the maximum value of f on AB. If that's the case, f min times b minus a has to be less than or equal to the integral, which has to be less than or equal to f max. In other words, if I have some function, let's make this extreme. F min, if this is A and this is B, F min times A minus B is the area of that rectangle. Whereas the area under the curve would go higher than that rectangle. Okay, so clearly this has to be less than the integral. But then if I add a third thing, and that is here's F max, and I make a rectangle that's F max tall, but B minus A wide, I clearly have something that's bigger than both of those other things. So F min times B minus A must be less than or equal to the integral, which must be less than or equal to F max times B minus A. And then lastly, if f of x is greater than or equal to g of x for all the values on that closed interval, that means the integral for f of x must be greater than the integral for g of x. Now, let's use some of these rules and go through this example. So for example, hey, we know that the integral from f of x from -1 to 1 is 5. The definite integral of f of x from 1 to 4 is -2. And the integral from -1 of h of x is 7. Can we find the value of the integral from 4 to 1? Well, we know the integral from 1 to 4, so this must be equal to the opposite of the integral from 1 to 4 of f of x dx, which means this is going to be -2. So that's -2, right? What about this next one? The integral from -1 to 4. Well, I know the integral of f of x from -1 to 1. I know, let me see if I can write legibly, that'd be good. I know the integral from 1 to 4 of f of x dx. So that area from -1 to 1 and then -1 to 4, they add up to the total area. So in this case, this is a 5 from that listing. This is a -2. Looks like this is equal to 3. Okay, what about this next one? The integral from -1 to 1 of 2 f of x and 3 h of x. Well, I can certainly think of this as the integral from -1 to 1 of 2 f of x plus the integral from -1 to 1 of 3 h of x. Put those dx's in there. Well, and then that constant multiplier can be pulled out. So integral from -1 to 1 of f of x plus 3 times the integral from -1 to 1 of h. 2 times that integral is 2 times 5. 3 times that integral is 7. So that's like 10 plus 21. That looks like that is 31. All right. Now, let's go to this next one. What about the integral from 0 to 1? Well, I have a -1 to 1. That's not 0 to 1, or 1 to 0 for that matter. I got 1 to 4. That doesn't seem to be helpful. Now, you may be tempted to give the answer 5 halves. This is half the interval of this one, but you'd be incorrect. This one, not possible. We don't have enough information to write out that integral's value. Same thing here. You might be tempted to say if it goes from -2 to 2, which is twice as big as the interval from -1 to 1, you might be tempted to say it's 2 times 7, but that one also be wrong. We don't know what's going on less than -1. We don't know what's going on as x goes greater than 1. So this is also not possible. And the last one, -1 to 4 of f of x plus g of x. Well, we've already found out the f of x part because we did this in part 2. But again, if this is the only information that we have about h, from -1 to 1, we don't have enough information to find out what's going on in that part. I'm going to list this as also as not possible to calculate. Let's move on to this next thing. Show that the value of the integral from 0 to 1 of 1 plus cosine x is less than 3 halves. Well, here's an idea. Cosine is always less than or equal to 1, no matter what the value of x is. We might say the expression 1 plus cosine x, therefore, can't get any bigger than pi over 2. All right? So what does that mean? Pi over 2 could be thought of as a replacement for f max. The width of our interval is 1. This is pi over 2. So here's my f max times b minus a, and it must be greater than or equal to, that's the largest it could be. So this integral must be less than root 2, which means this integral must be less than 3 halves, because 3 halves is less than root 2. Okay, changing gears. New definition, the average value of a function. We can find the average value of a function, if it's integrable, by finding the value of the definite integral of that function and dividing it by the width of the interval. Okay, in a sort of classic example, remember when I drove my car for 3 hours at 70 miles an hour and I got 210? Well, imagine me taking that 210 miles and dividing it by the width of that interval, which is 3. The average speed was 70. That's the same idea. Take the value of the integral and divide it by width, and then you get the average value of the function. So can we find the average value of this function on the interval from 0 to 3? Okay, so what is the integral from 0 to 3 of 4 minus x squared dx? And what happens when I divide this by 1 over 3 minus 0? So we are going to find the value of that integral. And I'm going to do that on the calculator, where the calculator has methods for starting with a calculator page. I'm going to go, I can go menu, calculus, integral, and it gives me a place to put in our numbers. 0 to 3 are the limits of integration. 4 minus x squared. So I'll put 4 minus x squared, and I'll put dx at the end. And it says the value of this is 3. Oh, I suppose I was supposed to divide that by 3. I suppose what I really should have entered is with the expression 1 over 3 minus 0 there. And we understand, of course, 3 divided by 3 is 1. Right? Great. So the value of this expression is equal to 1. Does this function ever take on this value on that interval? Is there a time where f of x really does equal 1? Well, let's try this out. 4 minus x squared is equal to 1. How about I subtract 1 from both sides and add x squared to both sides? How about I take the square root of both sides? Square root of 3 is equal to 2, equal to x. Now, of the two values here, negative root 3 and positive root 3, only one of them exists in that interval. So we're going to ignore that. Yep, the function f of x is equal to 4 minus x squared does equal to the average value of the function, 1, when x is root 3. All right. Now this is not surprising to us because we actually have a theorem that says somewhere, if a function is continuous, that there's some place in the interval where the average of the function, where the function is equal to the average of the function. And we call that the mean value theorem for integrals.